In this lesson, we will talk about physics and how it relates to calculus. So what you know is that the position function is s of t. S is the position of the body that you are looking at at a specific time t. And if you take the derivative of s of t, you will get the v of t, or velocity function. And if you take the second derivative of s of t, or that is the same thing as the first derivative of the velocity function, that will give you the acceleration function. And that all of these functions are will give you instantaneous positions, velocities, or accelerations based upon a specific time. Again, here with the average velocity, this happens over an interval of time, so from time A to time B. You can see that it is just finding the slope using the position function over a certain span of time. And then the last thing that I want to mention here that you already know is that speed is equal to the absolute value of velocity. One thing that I have not mentioned before is that this works for both average and instantaneous velocities. So if you're up here and you get a velocity instantaneously, or you find an average velocity, the speed will be the absolute value of either of those. On this slide, here is some more physics information. So this word I have not used yet. This is the word displacement. This just means the distance from the starting point, and this can be represented one of two ways. Either s of t plus delta t minus s of t, and this starts feeling like a derivative, what you've seen in the numerator for the limit definition of derivatives, or s of b minus s of a on the interval ab. So this is the numerator of the average velocity. And then the last thing down here, changing directions. Generally what you will want to do is you will want to find where v of t equals 0. And when you set the derivative of the position function or the velocity function equal to 0 and solve for t, you will find where the body is changing directions. Think like if you're throwing something up from the ground, it rises for a bit, and then when it reaches the maximum height, the velocity is 0 just for a second, or just for a moment, and then it starts coming back toward the earth. So finding where this velocity equals 0 is finding where the object changes directions. So in the examples in the coming slides, there will be many different scenarios where you need to find times and then substitute those times into other functions, or find displacements, or find an average velocity. There are just a lot of different avenues that these physics problems can burrow, and so I will present many of those in examples on the next few slides. Example: at any time t, the position of a body moving along the s-axis is s of t equals t cubed minus 6t squared plus 9t. Part A, find the acceleration at each time the velocity is 0. So what we are trying to do here is we have to find out where the velocity is 0. In order to do that, we need to find the velocity function. And since we know what the position function is, we can find the velocity function by taking the derivative. So the velocity function here will be v of t equals 3t squared minus 12t plus 9. And if we want to know when the velocity is equal to 0, you can set this whole function equal to 0 and solve for t. The first thing you want to do in solving for t is to divide everything by 3. You can divide all 3 terms on the left and 0 by 3. And you'll end up with t squared minus 4t plus 3 equals 0. And when you factor this quadratic polynomial and solve each factor, you will end up with t equals 1 and t equals 3. Now I want to stop here very quickly and point out that if you end up with a negative time, you have to throw that time away because you cannot travel backward in time. We can only travel forward in time. So both of these times are positive. They are in seconds. We have good times to work with. Now, for the rest of this, it says find the acceleration at the time the velocity is 0. So we have to take the derivative of this function. So I will take the derivative directly from this velocity function, not from a simplified function like down here. We have to use the velocity function. So that tells you the acceleration at time t equals 6t minus 12. And that's all by the power rule. And so what we have to do here is take each of these times separately, of course, and substitute them in for t everywhere you see t. So the acceleration at time 1, if you substitute 1 over here for t, you get 6 times 1 is 6, minus 12 is negative 6. And over here, if you substitute the 3 in for t, you will see that a at time 3 is positive 6. And I'd like to take a second here to explain that if there are no units, I mentioned over here that these are seconds. If there are no units, you can assume that the time is in seconds, and if there are no units, we just leave it generic. So this would be 6 units per second, or negative 6 units per second, or over down here, positive 6 units per second. Okay, part B. Part B asks to find the speed at each time the acceleration is 0. So we already know what the acceleration function is based on part A. So the acceleration is 6t minus 12. So since we know that the acceleration equals 6t minus 12 from above, we want to know when the acceleration equals 0. And that means you set this function equal to 0, and when you solve this for t, you end up with t equals 2. So that's great. We know when the acceleration equals 0, but we need to find the speed at that time. So the correct way to go about this is to use the velocity function. Again, not the simplified one. We have to use the original velocity function. So that is v of t equals 3t squared minus 12t plus 9. And then just like we did with the times over here, we have to take this time and substitute it in wherever you see t. So when you substitute 2 in here, you'll end up with the velocity at time 2 equals negative 3. And again, that's going to be units per second. But you have to remember that speed is the absolute value of this. So the speed will be positive 3 units per second. And I did goof just a little bit up here with acceleration. The acceleration units, the seconds in the denominator need to be squared. That's how acceleration is measured, units per second squared. So make sure that with acceleration you're giving units per second squared, and with speed and velocity you're giving units per second. So down here, final answer, 3 units per second. Over here, we had 2 answers. At time 1, it was -6 units per second squared, and at time 3, it was 6 units per second squared. On this slide, there is a continuation from the previous example. You are asked to find the displacement between the time equals 0 and time equals 2. So here is the position function again for your viewing pleasure. And what we need to do here is we simply need to find S of B minus S of A. And we already know that our time interval from over here is from 0 to 2 seconds, and 0 will be A and 2 will be B. And again, here we have a time equals 0, that's fine. Time can start at 0 and move forward to positive numbers, but not negative numbers, just so you hear it one more time. So we're trying to find S of 2 minus S of 0. And S of 0 in this case is really pretty simple. If you substitute 0 in for each t variable up here, you'll end up with 0. So this is minus 0. And if you substitute 2 in for all t values here, you'll end up with a value left over of 2. That is completely coincidental that you substitute in a 2 and you get a 2 back, and you substitute in a 0 and you get a 0 back. 100% coincidental. Anyway, the displacement here is 2 units. So what that means is that this particle, whatever we're looking at, starts here at time equals 0 and ends up 2 units away at time equals 2. So that means, I'm going to use a different color here, this particle could be starting here in yellow and traveling back and forth as many times as that and end up here 2 seconds later. Or that could mean that the particle just starts here and ends up here 2 seconds later. Displacement just means how far are you from the beginning point that many seconds later. So even though the yellow path traveled a heck of a lot more distance, it only ended up 2 units away from the original starting point. The pink path, even though it's a lot shorter, still ended up 2 units away from the starting point. For this next example, you are given the equation for free fall on the moon as S equals 3.76 t squared. The question then is, how long does it take for the rock to reach 30 meters per second? Now this over here, 30 meters per second, is a velocity. It is not a distance traveled, it is not a displacement, it is not an acceleration. This is a velocity, units per second. So that being the case, we need to find what the velocity function is from this position function. Well, you can use the power rule here to find the derivative of the position function, and you end up with the velocity function equaling 7.52 t. So how do you figure out how long it takes for the rock to reach 30 meters per second? Well, before, in the previous example, we were trying to figure out where the velocity was 0, so we set it equal to 0. Now we want to know where the velocity equals 30, so we take the velocity equation and set it equal to 30 meters per second. From here, if you solve this, it becomes a simple division. You divide 30 by 7.52 and you end up with a time being 3.989 seconds. And as a good rule, if you are asked an open-ended question, a non-multiple choice question, it's pretty safe to go out to 3 decimal places, or it will be specified how many decimal places you should go to. Round to the nearest 10th, round to the nearest 100th, round to the nearest so on and so forth. So I say 3 decimal places is good. Make sure you consult what the exercise is asking of you to know how many decimal places you should use. In this example, we have a different scenario. A rocket is shot upward from a 10-foot stand, and its height is modeled by S of t equals this equation. So the first thing you're asked to do here is to find the velocity and acceleration functions. Okay, that's not so bad. We just have to take the derivative of this function here. So we can take the derivative and get that the velocity is equal to the derivative of the position function, which is 50 minus 1.6 t, and that the acceleration function is the derivative of the velocity function at negative 1.6. For the next part, you are asked to find how long it takes for the rocket to reach its highest point. That is highest with 2 H's. So how long does it take for the rocket to reach its highest point? This is just in disguise asking you, where is the slope of the tangent line equal to 0? So what we can do is that we know the derivative of the position function is the velocity function. So if we're trying to find out where the slope of the tangent line equals 0, then we can set the velocity function equal to 0 and solve for t. So that is 50 minus 1.6 t equals 0. So you can add 1.6 t to both sides, divide both sides by 1.6 t, and get that t equals 31.25 seconds. Let me circle these answers up here to let you know that those are the final answers. So 31.25 seconds to reach its highest point. This next question asks, how high does the rocket go? And we already find out how long it takes for the rocket to reach its maximum height at 31.25 seconds. And if you want to find out how high the rocket went, all you have to do is substitute that into the position function. And if you'll remember from the previous slide, the position function is 10 plus 50t, and t in this case is 31.25 seconds, minus 0.8 t squared, and again t is 31.25 seconds squared. So after you simplify this product and this product down, you get these couple numbers here, and when you add up all these numbers together, you will end up with 791.25 feet. As I believe it was mentioned that feet is the unit. For part D, how long does it take to reach half its maximum height? So when the rocket gets launched, how long does it take for it to reach half of its maximum height? So we know that the maximum height is here, 791.25 feet. The first thing we need is half of that height. So 791.25 over 2 equals 395.625 feet, or 395 and 5/8 feet. So now that we have this as half of the height, we can take the position function, s of t equals, s of t equals 10 plus 50t minus 0.8 t squared, and set it equal to 395.625. And then you can solve this equation by using the quadratic formula, and you will end up with the following answers. The time being 9.012 seconds and 53.488 seconds. And you might be wondering why there are two times. Well, the rocket's flight, as it goes up to reach its maximum height of 791.25 feet, it has to pass the halfway point. And also, when the rocket is falling back toward the Earth, it also has to pass the halfway point again at 53.488 seconds. On the next slide, I will leave it up for about 10 seconds, is how the quadratic formula works for this equation right here. And lastly, the last question here, dealing with this one single equation, s of t equals 10 plus 50 t minus 0.8 t squared, is how long is it in the air? In other words, how long is the rocket in the air? Well, we know it starts at time 0. If you want to find how long it was in the air, you need to find where this equation equals, or where this function equals 0. So if you think about it, looking at it on a graph, this rocket is shot from 10 feet up in the air. It goes up really high, and then it's got to come back down. So if we can set this equation equal to 0 and find this time over here, we will know exactly how long it was in the air. So in order to do that, we will use the quadratic formula again. This polynomial will not factor, so we need to find the t using the quadratic formula. So I will slowly reveal some steps as to what that looks like. And so here you can see that through all of this quadratic formula work, where you multiply by 5 to eliminate the decimal, identify a, b, and c, set up the quadratic formula, simplify the square root, add these two numbers and divide by -8 to get this time, subtract these two numbers, divide by -8 to get this time. Again, you cannot have a negative time, so the rocket lands at 62.699 seconds later.